Good morning, all. So welcome to our second day of the conference. So let me just recall the announcement that I gave yesterday. That is, remember that we need to wear the FFP2 mask besides the speaker. Remember not to leave items unattended in the room, and also to keep the badge with you. So now I'm calling the chair of the first speaker of today, Martino Bardi, please.
So good morning, everybody. Welcome to this second day of this very nice meeting. It's a real pleasure for me to be the chairman for Alberto Bressan. Alberto Bressan was a student in Padova in the 70s with me, and he got a PhD in Colorado, and then he came back in Italy, and his first permanent position was again in Padova for 4 years in the middle of the 80s. Then he held positions again in Colorado at CISA, where for 10 years he had lots of students, and then now he is in Penn State, Pennsylvania. Alberto is famous for a fundamental contribution he gave to gas dynamics. At the end of the 80s, he started working on the problem of well-posedness of hyperbolic nonlinear systems of a partial differential equation, of conservation laws, which are fundamental in physics. And in a series of papers, the first 3 or 4 by himself, and then with his students, he really settled the complete theory about well-posedness of such systems, and which is now summarized in his monograph called Well-Posedness of Hyperbolic Systems of Conservation Laws, which is a fundamental reference in the field since then. He got several prizes. I don't mention all of them. Let me mention the Feltrinelli Prize in 2006, the Bocher Prize of the American Mathematical Society in 2008, the Fichera Prize of the Italian Mathematical Union in 2011. As I said, he had lots of students. I counted 26 on his CV. Some of them are here. One is Benedetto Piccoli, first row here. And another important one is Stefano Bianchini. So he really did a very important work in partial differential equations and also in optimal control. And today, in fact, he will speak to us about about control problems in Lagrangian mechanics. Please, Alberto.
Well, thank you. So it's really a pleasure to be back in Padova, especially in this particular occasion. And for this, I would like to thank the organizer and all the people whose work has contributed to make this event happen. So for today, I decided to talk about control in Lagrangian mechanics because, first of all, it is a topic to which various people here in Padova have contributed, and also for me, it provided a way to keep connected with the University of Padova. So in the end, I leave it to you to decide whether this is really high-level mathematics, but here I would claim that at least it is high-altitude math, because at least part of this theory was originally conceived high up in the Dolomites along the ski slopes between Folgarida and Madonna di Campiglio. And here, just to introduce the topic, I'm showing 2 different types of ski slopes. So on the left, you can see a large downhill trail. I think this is a photo from Madonna di Campiglio. On the other side, you have one narrow trail with just 2 parallel ski tracks, and these are the trails which are used to connect different downhill trails. And here is where the problem comes about. So you have one skier that I'll call skier A, And he's coming down on a wide trail, so he has plenty of room to maneuver. He can turn, he can even stop if he likes. However, he does not see skier B because he's hidden behind the trees. And on the other hand, skier B is the one on the narrow trail. He's aware that he's about to join the intersection with the main trail, but he has no way to reduce his speed because he's just following the two parallel tracks. And in a situation like this, it turns out that at times the collision is unavoidable. And this is well documented in the literature. And for example, this is from an analysis of the trajectory for skier A, the one from the left on the large downhill trail. But let us focus now on skier B, because it's really skier B the one that motivated much of the theoretical developments that I want to discuss today. So this is skier B at the initial time t0. As you can see, he's planning to use his ski poles to produce a force that will increase the velocity of his barycenter. And okay, here's again skier B at a later time where his kinetic energy is approaching its maximum value. And here again, it's skier B. And as you can see, skier B is very confident on his technical skills. Unfortunately, he's not aware about the theory of controlizable Lagrangian coordinates, which will be developed at the University of Padua only decades later after this picture was taken. And as a result, as he approaches the intersection, well, he realizes that he is traveling with excessive speed, but it's too late. You see, he's trying to reduce his speed, but his control strategy is not very effective, and the crash is inevitable. And we have experimental data that shows that after collision, skier A is in no better shape. So we shall never know the true names of skier A and skier B that collided somewhere along the trails of between Folgarida and Madonna di Campiglio, sometimes in the 1980s. But what is certain is that they produced a deep impact, that is, on the development of Lagrangian mechanics at the University of Padua, because it was after witnessing this unfortunate event that Aldo Bressan, that is my father, started a research program with the aim of understanding what are the optimal strategies for controlling the speed of skier B. And the initial results of this investigation were published in two long memoirs by the Accademia dei Lincei in Rome. So as you can see, the first one is on hyperimpulsive motion and controlizable coordinates for Lagrangian system. That is kind of the general theory. And the second one, still about 50 pages long, is about application to the control of the ski and swing. Okay, so let me start by sketching what are the ideas behind these works. So there are two different ways of controlling mechanical systems. The natural one is just to add external force. For example, if you have a child that is riding on a swing, the one on the left, one possible way to control this is if the mother is pushing him. So that would be controlled by an external force. On the other hand, an older boy could ride the swing without anybody pushing him, and he could pump energy into the system just by standing up or bending down. So in this case, what he can do is change the position of his barycenter. So in the case on the left, we have a system with 2 degrees of freedom. You can think of one coordinate is the angle and the other is the radius of oscillation. So by standing up or bending down, he can change one of these coordinates, that is the radius of oscillation, and assign this as a function of time. And then from the equations, you can recover the motion of the other variable, which is the angle. Okay, so what is the general framework? So we have a Lagrangian manifold with variables q1, qn. So we have a kinetic energy, which is a quadratic form in the derivatives of the variables q, qi, qj. So this is the quadratic form that determines the Riemann metric on the manifold. Then we have a potential energy and the Lagrangian function. So if we want to control the motion by adding external forces, then the equations are classical. You can, I think everybody here has seen this in a course in rational mechanics. So these are the Euler-Lagrange equation with some force, external force, as source term on the right-hand side. On the other hand, one can also control a Lagrangian system by assigning some of the coordinates as functions of time. And here the framework is as follows. So we have n plus m coordinates, but of these, we split them into 2 parts. The first n will be the free ones, and the last m coordinates will be assigned directly as function of time. So we can think the last m coordinates, which are these ones, are actually control. There are ways to control the system. And once we assign these as functions of time, what we need is to determine the first n coordinates by the equation of motion. And how can this be done? Well, first we have to make a fundamental assumption, that is that these identities, for which we impose these constraints, time-dependent constraints, these are implemented by frictionless constraints. So what does it mean? Well, see, if I fix these variables here from qn plus 1, qn plus m, and I let the other ones vary, I get one particular submanifold. I call this lambda u. Okay. So every assignment, qi is equal ui, determines one particular submanifold, a leaf of this foliation. And the key assumption is that the force that moves that is implemented to push the system from one leaf to another leaf is always perpendicular to the leaf itself at every point. Okay. So if we do this, then we can derive the equation of motion as follows. So it turns out that it's more convenient to write this equation in Hamiltonian form first. So we start with these Lagrangian variables, which are n plus m, and we write the conjugate momenta. So if we don't have any constraints, we would have a system, a Hamiltonian system of n plus m equation for the qi and n plus m for the pi. And now we want to reduce this system to a smaller system that involves only the first n q's and the first n p, right? So within these ones, we have to substitute the values of the remaining q and the remaining p. So the remaining q is trivial because these are assigned by the constraints. So qj will be equal to uj of t, that's the control, and that's it. And then we have to determine these pj as functions of the remaining p1, pn, and the derivatives of these control functions. Okay, here I'm skipping details. Of course, I don't want to go through all the derivation, but what is the final product of this analysis? So we have a kinetic energy matrix. So this is a symmetric matrix of n plus n rows and columns. So we partition this in 2 parts. So the first part corresponds to the uncontrolled variables, and the last part corresponds to the control variables, those assigned as functions of time by active constraints. So out of this, we consider the matrix A, which is the inverse of G11, and then we form these other two matrices. K is minus A times G12, which is this one, and then B is G22 minus G21 A G12. So this is a combination of matrices, and in the end, the equation that determines the evolution of the three variables, Q dot and P dot, has this form. And as you can see, what is relevant here is that these equations are either linear and also they can be quadratic with respect to the derivative of the control functions. Okay. So here U, U1, UM are the control function, and if there are additional external forces, they come in here. Okay. But in the end, what is interesting about this derivation is that there is no need to actually compute these forces that are used to implement the constraints. Okay, we can just derive the equation without this. So, what kind of evolution equation we get in the end? Well, you can think of x, just for notational simplicity, let me call x the vector q1, qm, p1, pn, and the vector of controls. So in general, we get this type of equation, which is where the right-hand side is quadratic with respect to the time derivatives of the control functions. But there are very important, very interesting special cases where these quadratic terms vanish, and that we call fit for jumps. And the name comes because, well, in this case, it is possible to define the motion of the system also if U is a discontinuous function. Because in this case, well, UI dot will be like a Dirac delta function, but still it makes sense. Okay. While if U is discontinuous, in this case, this will be the product of two delta functions, which does not make any sense. Okay. And then we could also have the case of strongly fit for jumps. And in this case, you can completely eliminate also the variable, the dependence on the time derivatives U dot. And so in this case, you get just a completely standard control problem. Okay. So what are the main issues that we want to investigate about this type of systems? Well, first of all, we want to understand the relation between the analytic form of the equation, that is linear or quadratic, compare this with the geometric properties of the foliation, and also we can take a topological point of view, that is, determines what are the topologies that render continuous the control to trajectory map from U, from the set of controls, to the set of trajectories. And of course, this is very first set of questions, and then of course we can study controllability, stabilization, and optimization problem for this type of systems. Okay, so what is the geometric picture? So within the Lagrangian manifold M, we can consider a foliation, as I said before, whose leaves are obtained by freezing the values of these controlled coordinates. So if I fix the value of Qn plus 1, Qn plus 2, Qn plus m, I get one of these submanifolds. And now, what is the relation between the geometry of these submanifolds and the fact that these equations are linear or quadratic? Well, it turns out that this hyperimpulsive system is fit for jumps, that is linear with respect to U dot, if and only if this foliation is bundle-like. That means the leaves remain at constant distance from each other. So if you look at one of these leaves and then another leaf, the distance between these two is the same at every point. Equivalently, we could say that any geodesic gamma that starts perpendicular to one of these leaves, it crosses all the other leaves still perpendicularly. Okay, so these are all geometric equivalent properties that ensure that the equations are linear with respect to the derivative of a control, so fit for jumps. This is another example where the foliation is not fit for jumps, and in fact you can immediately see that the distance between any two of these leaves here is not constant, because here they are very close and here they are far apart. And if you look at any geodesic, which is a straight line here, if this crosses this lambda u perpendicularly, it does not cross perpendicularly the other ones. Okay. Then when is this system strongly fit for jumps? When you can completely eliminate also the dependence on u dot. Well, this is the case if, in addition, the distribution perpendicular to the leaves is integrable. So in this picture, let's think that the leaves are these curved lines here, lambda u. For a fixed u, I have this vertical curve, which is one particular leaf. And I look at the distribution, so the set of, think of the set of planes which intersect lambda u in a perpendicular way. Okay, so this gives a distribution, and if this distribution is integrable, that is, if I can find either some submanifolds which contain all these perpendicular distributions, then it would be integrable. But in this case, for example, it's not integrable, because if I take for example, a closed curve here, and I move perpendicularly to each leaf, and then eventually I come back to the same initial point u, here the corresponding trajectory does not reach the same point on the leaf lambda u. Okay, so that would be a distribution which is not integrable according to Frobenius. So in this case, it's not strongly fit for jumps. Okay. So for the very simplest example that I can think of in this direction is the following. So think of a bead sliding on a rotating bar, and here is, on the other hand, is a swing with variable radius of oscillation. So in both cases, we have a system described by two coordinates, polar coordinates. That is, one is the angle and the other is the radius. But in the first case, we control the angle, so we assign the angle as a function of time. So think of a rigid bar. And then we want to determine the position of these beads that slides along the bar without friction. And in this case, it turns out that this is not fit for jumps. In fact, if you give a sudden change in the angle, it shoots out at infinity, right? On the other hand, this is fit for jumps, because if you assign the radius as a function of time, and then determine the angle, this makes sense. You can solve the equation of motion even if the radius has an impulse, if this continues, right? And well, you can see the corresponding equation here. So in the first case, if you assign the radius, which would be this case, you see u dot comes only linearly, and this would be fit for jumps, because if you look at the foliation, the leaves have constant distance from each other. On the other hand, if you assign the angle, in this case, you can see that u dot appears quadratically in the equation, and this is a typical case where the system is not fit for jumps. In fact, these leaves, which are these rays here, do not keep constant distance from each other. So next, what are the topologies that render continuous this input to trajectory map? And of course, these also depend a lot on the form of the equation, because if the equations are quadratic with respect to the derivative, of course, it's clear that this derivative u dot must be square integrable to make this meaningful. So this map would be continuous if u is chosen on the space H1, so with first derivative in L2. On the other hand, this is the most interesting case. which we call fit for jumps. In this case, see, we want to define a solution also when u is possibly discontinuous. So u dot would be a delta function. But in this case, there is some ambiguity because in this case, gi depends on u and u is discontinuous. So we would have the product of the discontinuous function times the delta function, right? So to make this meaningful, whenever u has a jump, we have to assign one particular path to move from, let's say, u minus to u plus, from the limits from the left and from the right. So one possibility to do this is to reparameterize the graph in a Lipschitz continuous way, say from S to T of S, U of S. So whenever U has a jump, we kind of bridge it with a continuous Lipschitz curve that moves from here to here, and then we solve this ODE for the new variable S. Okay, let's see how am I doing. Okay, so what kind of continuous dependence can we expect with this definition of solutions when u dot appears linearly on the right-hand side? Well, the control to trajectory map, in this case, can be rendered continuous with respect to a distance defined by taking the infimum over all parameterization of these graph completions. So, see, let's say I have these two functions. One would be u1 and the blue one would be u2. And I make a graph completion. So every time that my function has a jump, I bridge it by a continuous vertical line. And then what I have to do is look at a parameterization of the blue line and a parameterization of the red line and take the maximum distance between these two values at the same S. Okay, so in this case, I look at the maximum length of these segments. Okay. And then I take the infimum over all possible ways of reparameterizing these two paths. Okay. And in general, this is much smaller than actually the L infinity distance between these two functions, because if I look at the L infinity distance would be pretty much the length of this vertical segment. And in fact, if I take the infimum over all reparameterization, I get the maximum among the length of this segment, which is in fact much smaller. Okay. Yeah, and this appears on one of my joint paper with Franco Rampazzo. And okay, here, since if I have some time, I want to describe a spin-off of this theory, which is to hyperbolic system of conservation laws. So, as was mentioned before, a hyperbolic system of conservation law is a PD in this divergence form. So U can be a vector. F of U is U is the vector of conserved quantity. F is the vector of fluxes. And you can write this in quasi-linear form, where A is the Jacobian of matrix of F. So for continuous solutions, this system is the same as this quasi-linear system here. However, for the original one, we can also consider discontinuous solution where U has a jump. For example, U of Tx is one value, U minus on the right, on the left, and U plus on the right. So U minus if x is less than lambda t, U plus if x is greater than lambda t. And this describes a shock which is traveling with speed lambda. And actually, since the time of Riemann, I guess, we know that it's possible to make sense of a solution of this type of equation also for discontinuous functions, and this is the case. This is a solution in distributional sense if the speed of the jump satisfies these famous Rankine-Hugoniot equations. So what happens if we want to consider now an equation in quasi-linear form where A possibly is not the Jacobian of a flux function. Okay. So in this case, actually, what we can do is whenever we have a jump, we can, again, bridge the jump by graph completion. So draw one particular path from U minus to U plus, parameterize this path, and define this non-conservative product, AU times UX, which I recall this is a discontinuous functions time a delta mass, and we can define this by integrating along this path. Of course, if A is not the Jacobian of a flux function, then this product that we obtain strongly depends on the choice of this path. Okay? And but in this way, if we have some natural way to choose a path, for example, we could choose just the straight segment that connects the 2 points, then we can define still discontinuous solution to non-conservative hyperbolic systems. In this way, just replacing the Rankine-Lugonier equation at jumps with this relation here. So instead of f of u plus minus f of u minus, we just write this integral here along a path. Okay, again, this depends on the particular path, of course. And there are works by Rampazzo and Dalmaso, and then Dalmaso, Lefloc, and Murat that consider this type of definitions, and this has given rise to a very large amount of literature on these so-called non-conservative products. Okay, and as I said, there are many issues that can be considered, studied about this impulsive control system. So in general, the general form would be like x dot is equal some function that depends on x, depends on the control function u, and also depends on the time derivative of the control function u. Okay. And so if we assign one initial data, there are many issues that we can study. So one is the limit of trajectories corresponding to smooth controls, and how we can characterize this limit of trajectories that we could call kind of relaxed trajectory of the original system. And one way to study these is to represent them as a solution to a differential inclusions, possibly with unbounded right-hand side. Then we can study most of the things that we can also study for standard control systems, that is, Lie brackets, study controllability, study stabilization problems, then studying optimal impulsive controls, existence, necessary condition for optimality, minimum time function, Hamilton-Jacobi equation for the value function, and so on. So these are all problems that we usually study also in the classical theory of controls, but the fact that here we have dependence on the derivative, so the system has impulsive nature, it provides some additional challenging and has novel features in these works. And as I mentioned at the beginning, there are several people also in Padova that work on this topic. Here I'll just mention Franco Rampazzo, Caterina Sartori, Monica Motta, Soledad Aron, Franco Cardin, Marco Favretti, Francesco Passò, Marta Zoppello, and I apologize if this is only an incomplete list. So in the remaining part of this talk, I want to mention that this theory of controlizable Lagrangian coordinate can also be applied to describe a class of problems in swim-like motion in a perfect fluid. So here the idea is that we consider a deformable body whose shape and internal mass distribution are described by finitely many parameters. Okay? So we want to assign some of these parameters as function of time and then determine the motion. Okay? So we want to control the position of these deformable bodies by, say, assigning the shape as function of time. And in this way, well, it's like a fish, right? It changes its shape, and this way it can move, right? So what kind of equation do we get? in this setting. So the basic framework is that we have a reference configuration for this moving body, which is this omega. And each time t, the position and the shape of the body will be described by a finite number of Lagrangian parameters. And each value of these parameters determines a volume-preserving diffeomorphism. So if you choose one value for Q1, Q2, Qn, this in particular determines a diffeomorphism that preserves the volume. Okay, so for example, this point psi would be sent at this point here, and so on. Okay. So the kinetic energy of the body, of course, will be determined by some quadratic form in terms of the time derivatives of the Lagrangian variable, as usual. But now the point is that we also need to incorporate in our equation the kinetic energy of all the surrounding fluid. Now in general, the motion of a fluid is something that involves a vector field defined outside the body, which is in an infinite dimensional space, of course, a vector field. But what is special in this case is that if the deformation lie in a finite dimensional manifold, also the vector fields describing the velocity of the fluid outside, they live in a finite dimensional manifold. So we can have a finite dimensional reduction of this problem. So how is the kinetic energy of the fluid? Of course, this would be the integral of the velocity of the fluid integrated, well, square over 2, integrated over the complement of the region occupied by the body. Okay. And I claim this can also be written as a quadratic form in the time derivatives qi, qj. Okay. How do you do this? Well, of course, we have to make strong assumptions to achieve this. So we assume, for example, that the fluid motion is in R2, zero vorticity, zero circulation. So given Q and Q dot, we seek the unique, incompressible, irrotational velocity field defined on the complement outside the body, such that its perpendicular component at every boundary point, phi q of psi, satisfies this relation here. Okay? So it means that if you look at the velocity v of the fluid at any boundary point of the body, the inner product of v with the outer normal is the same as, well, is the velocity at which the surface of the body moves. Okay. So how do we solve this equation? Well, in this setting, it's pretty simple because since it's irrotational, we can write v as the gradient of some function psi. This is not a spring function, but it's an equivalent function. So we can solve the Neumann problem in the exterior domain. So it's Laplacian of psi is equal 0 outside with these Neumann boundary conditions. And this, in the end, yields a finite dimensional Lagrangian system in these finitely many variables. And the difference, really the only difference, is that the kinetic energy now is the kinetic energy of the body plus the kinetic energy of the fluid. And this can still be represented as a quadratic form with respect to the time derivatives of the Lagrangian variables. And here the most important principle to keep in mind is the following, that when is this particular system now fit for jumps? Okay. It turns out that it's one sufficient condition for it being fit for jumps is that if these controlled variables completely determine the shape of the body and the internal distribution of masses up to a translation and a rotation. So the position of the body up to translation and rotation is determined by the assigned control variables. The free variables simply determines the position up to a rotation of how it's translated. In this case, it's fit for jumps. And well, here I'll just give a couple of examples that were, of course, considered in earlier literature to which this general theory would apply. So this is an old paper by Safman on recoiling and squirming. So, for example, on the left, we have an example of a body. The shape of the body depends on only one parameter, which is, it's always an ellipse. What changes is the eccentricity of the ellipse. Okay, first is elongated horizontally and then becomes more elongated vertically. And the second parameter is the position of a mass inside this body. And by moving these two control parameters, we can, in fact, generate a Lie bracket, and that produces motion. For example, first we take this mass, we move it to the left, and so from here we get to this position here. And then from here to here, we change the eccentricity. From here to here, we again move the mass to the right, so we are here. And then again, we change the eccentricity. So it's kind of generating a Lie bracket between these two controls. And in this way, after a whole cycle, the body moves, not by much, but at least some positive epsilon. Okay. This is another squirming. This is another example where the density inside the body is constant, but the shape of the body changes depending on two parameters. Okay, so you can first elongate in this direction, then become an ellipse, and then it gets this shape, and after a whole cycle, it's still a circle, but it has moved a little bit. So this is an example where you can, again, obtain Lie brackets, and thanks to these Lie brackets, you achieve motion. Another cute example that was investigated by Kozlov is the following. So assume that you go fishing, but at some point, the engine in your boat breaks down, so you're stuck in the middle of the lake. How can you get home? And the solution is that, in principle, you could just walk home. That is, walk around your boat. In fact, the boat is two-dimensional, so you can walk forming, again, Lie brackets, loops. And believe it or not, you can indeed control the position, and very, very slowly, this boat would move in one direction. So if you are very persistent, well, you should be able to reach the shore. And this is, again, fit for jumps because the shape is completely controlled, and also the mass distribution is precisely what we control as a function of time. Yet another examples by Kanso, Marsdell, and Rowley, Melly Huber, a number of authors. They consider a snake-like change of three ellipses in a perfect fluid. So here, these bars are rigid, but what you are controlling are these two angles, A, alpha and beta. Okay, so again, by controlling these two angles, you control completely the shape of the body, and the free parameters are the position of the body up to a translation, in fact, and a possible rotation. And it turns out, again, that this is a system fit for jumps, and it's completely controllable. Finally, two examples of fit systems which are not fit for jumps. So think, for example, as two flapping fins, but here alpha and beta are free angles, and what we are controlling is only this distance r between these 2 points. So we can push them together, closer together or farther away. But you see, in this case, we do not control the shape of the body because, in fact, these two angles are free. And it turns out this is not fit for jumps. And another example is this chain of buoys pulled from a point. Again, think of these as rigid bars connecting the three buoys, but the angles, beta and gamma, are free. Okay, so these are not control variables. What we control is this point PT, so we are just pushing or pulling the end of this bar here. And so the system is determined by, well, the position of the point P and these three angles, alpha, beta, and gamma. So if P is just the only variable that is controlled, this is, again, not fit for jumps. Okay. And you can find a survey of these topics on one of my probably most recent survey papers here, 2008. Okay, so I'm approaching the end of this talk, and I realize I should tell you again what is the optimal strategy for the skier on a narrow trail. So this is a system governed by two Lagrangian parameters. One is the arc length along the trail, of course, I denote by S, and the other is the height of the body center. So the height is the control variable because the skier can either bend down or stand up, okay, at any given time along the trail. And then we want to compute the evolution of the remaining free coordinate S as a function of time. So what is the optimal control, optimal feedback control? Well, let's say that we want to maximize the velocity of the skier, okay? So the optimal control would be either stand up or bend down, switching at the points where either the inflection points or these horizontal points. More precisely, so let's say that we have a feedback control that ranges between a minimum height and a maximum height of the body center over the trail, okay? And it turns out that the optimal control is indeed bang-bang. So you can either have h of s is equal the minimum or the maximum, and the switching points are the points where either the slope changes sign, so these points, so here is going downhill, here is going uphill, okay? So at these minimum or maximum points, you switch, actually you always stand up, and you bend down at the points where the curvature changes sign. So here it's concave down, and then here is concave up, and this is inflection points. Okay, so you bend down at inflection points, and you stand up at the points where the slope changing sign. This if you want to maximize the speed. If you want to minimize the speed, you do just the opposite. So you would bend down here and stand up here. Okay, and this is in fact what was found in this original paper by Aldo Bressan in 1991. If you look at the last page, you find this optimal strategy. Okay, so I conclude here. So if you understand this, in fact, everything else in the art of skiing is really very, very simple. Thank you for the attention.
Thank you very much, Alberto. Questions or comments from the audience? At home, anybody asking questions? No. Are there some people applying these ideas to so, I don't know, robotics or some kind of real mechanical systems, like for the swimmers producing little robots that swim by themselves?
Well, I believe so. I know of the work of De Simone, for example, that he had like 3 discs, and he made different devices, and he even made movies of competitions swimming competition on this different swimmer, but this is still a game for mathematicians, I must say. But in fact, there are, of course, a lot of application to various things. I know that my father has contacted at some point the ski team and checked the manual for skier written, and since it was written by an engineer, he found a lot of mistakes in basic principle of rational mechanics in this. I don't know, I don't remember what happened after that, but
Okay, thank you. Other questions?
Thank you very much. Is there any connection between being fit for jumps or not and controllability? Yes or no? Is there any way to connect the two?
well, in both cases, you certainly can study controllability problems. It is very different, this type of equation, because if it's not fit for jumps, it means that you can give a tiny oscillation, and this will kind of move the system very fast in one direction. So it's like you have one particular direction in which you can move instantaneously. Okay. And then you can use this for controlling your system. You cannot use this strategy if it's fit for jumps, of course. It's different settings, but in both cases, indeed, you can study stabilization and controllability.
Okay, thanks.
Other comments or questions? Okay, if not, I thank again Alberto for a very nice talk.
Okay, for the first time, we are a bit ahead in the program, so we'll resume in 7 minutes. Okay, so please take seat that we resume our session. And so I call Bruno Chiarellotto to chair the second speaker of this morning session. Please, Bruno.
Good morning, everybody. The next speaker is Professor Peter Scholze from the University of Bonn. As a young mathematician, he won 3 gold medals for international mathematical Olympiads. He studied at the University of Bonn, where he obtained his PhD in 2012 under the supervision of Professor Michael Rapoport. His thesis is a milestone in arithmetic geometry. In 2012, the same year, just after his PhD, he was made a full professor at the University of Bonn with the Hausdorff Chair. 24 years old, one of the, perhaps the youngest professor in Germany, and not only there, I think. Between 2011 and 2016, he was a research fellow at Clay Mathematical Institute. In 2014, he was invited in Berkeley, and he gave a series of lectures, which now they are all collected in a volume called the Berkeley Lectures on P-adic Geometry. In 2018, he was indicated as a director of the Max Planck Institute in Bonn. Other than the field medals in 2018, Peter Scholz was awarded by the Cole Prize in 2015, the Prix and the Cours Pecot at Paris, the Leibniz Prize, and he received the Great Cross of the Order of Merit of the Federal Republic of Germany. The work, let's speak about the work. He won the field medals for the groundbreaking contribution to arithmetic geometry, which were made during his thesis. He introduced the theory of perfectoid spaces. He was able to make a concrete bridge between characteristic 0 and characteristic P in the p-adic fields. In this setting, following the work of some other field medals like Grothendieck, Deligne, Faltings, and many other big mathematicians, let me remind Fontaine and Rappaport too, he was able to deal with long-standing problems, like the weight monodromy conjecture, the generalization of the almost purity theorem, not to mention his big work in the direction of the Langland programs. Then, in all of these, he was using his theory of perfectoid spaces and also introducing some other tools like Pro et al. Topology. Later, Peter Scholz started to develop new theory like diamonds and prismatic homology. The aim was to build a workable bridge, again, between a singular cohomology, the RAM cohomology, L-adic cohomology, and the p-adic, let me say, crystalline cohomology. The results were, again, remarkable. Recently, he started a new theory, what is called the condensed mathematics. Now, the bridge is towards also classical geometry, let's say real numbers. So let's listen to him in his talk. Thank you very much.
Well, thank you. Can you hear me? Okay, you can hear me? Just to be sure.
Yes, we can hear you.
Okay, great. Thanks a lot for the introduction. I was very much looking forward to coming to Padua this week. I haven't been, and I would love to be in this magnificent aula that you're in. Well, but then I got COVID just recently, and you will still hear me coughing a little bit. I'm recovered, but well, I don't want to take any risks. So yes, I want to talk about this work that's all, I should say, joined with Dustin Clausen. On condensed mathematics and the applications that we have of this formalism to doing analytic geometry. And to get started, so like all my mathematical life, basically, I've spent in this very strange world of the p-adic numbers. But like for in number theory, you're also interested in the integers and also in the real numbers. And so at some point, I somehow hope that the techniques that I'm using in p-adic geometry, that there's also some version of them that could work in like the more familiar settings of the real or complex numbers. And indeed, by now, something like that works. And so we can really revisit very classical complex geometry now from this perspective. And this is what I want to talk about a little bit today. And so let me start with like some very, very basic complex analysis, okay? So in complex analysis, like in one variable, let's restrict to one variable for simplicity. So we have this thing that for any open subset, U of the complex numbers, we have the notion of a holomorphic function on U. Sometimes it's also called like complex differentiable. Function on U. And they form such holomorphic functions, and naturally you can add them, you can multiply them. They form a topological, it's actually some kind of Fréchet algebra, algebra of the complex numbers. That's often denoted by O of U. So O of U, these are those functions f from U to C that are complex differentiable. And this has two key properties, this kind of notion of a holomorphic function. One is that it's local, in the following sense, that if you have a cover of U by some other open subsets UI, then you can somehow define a holomorphic function locally. To define a holomorphic function on U, all you have to do is define holomorphic functions on all the UIs, and of course on intersections they should agree. So then O of UI is just a collection of all functions, holomorphic functions on all the open subsets, such that when you restrict to intersections, they agree. Okay. So in like fancy terminology that says that this thing O is a sheaf. So a sheaf is something on this topological space C. So a sheaf is something that associates to any open subset some value, which would be this O of U. When you have a further subset of U, there should be some restriction map, so you should always be able to restrict such functions. And then this is really the key axiom here of being a sheaf, that it's something that's locally determined. To get something on U, you just have to define it on the UI with this property. But on the other hand, it's also has some kind of global rigidity. So there's some kind of global convergence in the following sense. If U is some disk, so it's a set of all complex numbers of distance less than r to some point. You have your complex plane, you have some point x here, and then you have some radius r, and then you have this disk. Then you can actually very, very explicitly say what this O of U is. Namely, O of U are just all those power series expansions centered at x, so an times t minus x to the n, which are globally convergent on this disk. So you can, I don't know, it's some explicit growth condition on the coefficient. So for all r prime less than r, an times r prime to the n goes to 0. And it's actually a highly non-trivial fact that you can have these two properties simultaneously. Okay. So to have these simultaneously, we need the following theorem. That if you have, well, let's say just the disk around 0 of radius 1 for simplicity, to C admits such convergent power series expansions locally around any point. Around any point, it's called X again, in this disk. Then it also admits such a power series expansion. I mean, then f of z admits such a global series expansion. So, where this goes to 0 for all R and so on. And so, I mean, this is a theorem that was known for a very, very long time, but already back in the days, like Weierstrass thought it's an important problem to somehow get a pure sort proof of this. And I think so far there's still somehow no pure sort proof of this. So let me explain the way this is usually proved. So the usual proof uses this like integration around circles. More precisely, there's some other theorem that. So what do we have to prove? So assume. So given f as above, I mean, we have a power series expansion near, we have a power series expansion near 0, but we a priori don't know that it somehow satisfies this growth condition on the coefficients. So that'd be the power series expansion. At 0. Then for all loops from gamma from S1 to this disk, let's say winding once around the origin. Sorry, minus 0. You can integrate along this path, you can integrate f of z over z to the n dz. And then this would be, I guess, 2 pi I times a n minus 1. Probably. I hope that's right. yeah, so you have your disk of radius 1, and then you take any path, I don't know, gamma, that doesn't hit the origin and goes once around the origin. And then for all such, you can do this funny integral of integrating such a function against over this region, and then turns out that this gives you one way to actually compute the coefficients of this power series expansion. And you prove this by deforming gamma. Until it is close to 0. And then you compute. Now the key fact about complex differentiable functions is precisely that when you deform such a path of integration, such an integral doesn't actually change. But there's really some analysis that's going on here, that you somehow analyze the infinitesimal behavior when you change the gamma, and well, you need to perturb this path, and yeah. Okay. But once you have that, you can actually use this formula to get the desired estimate on the coefficients. So then take for gamma the circle of radius r. And then you can just estimate that 2 pi I times an minus 1. It's bounded by integrating over the circle 1 over r to the n times the maximum over the circle. That will see for all n. So Rn times the absolute value of an is bounded. If you rearrange this a little bit. And if Rn times the absolute value of an is bounded for r less than 1, then, well, by taking r slightly larger, you also see that these must go to 0 actually for r less than 1. Okay, so that's the usual proof. But I mean, this is about complex analysis, and there is some of the similar theory of p-adic analysis. In p-adic analysis, there's a similar theorem, but the proof is completely different. And I mean, even the notion of integrating a function along the path doesn't really make good sense in p-adic geometry. Like all the notions that are used in this proof, they don't really have a p-adic analog, and the proof in p-adic geometry is completely different. So if you want to try to somehow unify like the p-adic stuff and the real complex stuff, then you need to find, well, some way to make them more similar to each other. And we're not trying to make the p-adic stuff more similar to the complex stuff, but instead we're trying to make the complex stuff more similar to the p-adic stuff. And so, yeah, so I want to explain a different proof that completely avoids any talk of integration. And so this was also a problem that was on Weierstrass's mind, how to prove this without talking about integration. And there are some proofs in the literature where, in effect, just this integral is disguised in terms of finite sums or something like this. So, I mean, but I think all proofs are just some variant of this proof. This is completely unlike the p-adic proof. And so the goal is to prove this without integration. So this challenge goes back to Weierstrass. Okay. And so the key input in order to make this work is to have a very, very good framework for talking about such topological algebras. So our proof will sometimes be of an extremely algebraic nature, but in order to make these extremely algebraic or categorical arguments, we need to be able to talk about things like holomorphic functions, which are naturally some kind of topological algebras. We need to be able to talk about them in a very categorical, in a very algebraic manner. Logical vector spaces or topological algebras. So we will somehow really analyze these algebras of holomorphic functions and their properties in some direct kind of categorical manner. And so this is offered by, and so for this, the key is to replace topological spaces by something slightly different, by what we termed condensed sets. So the idea is that there are certain topological spaces of a very algebraic nature. And these are the totally disconnected compact Hausdorff spaces. For example, the Cantor set. So there are several different ways of thinking about this class of topological spaces in a purely algebraic way. So these are often called stone spaces. And one way to think about stone spaces is by stone duality. So they exactly correspond to the class of Boolean algebras. But there's a contravariant correspondence. So whenever you have such a totally disconnected space, you can consider the Boolean algebra of open and closed subsets. So this gives you a Boolean algebra, and conversely, any Boolean algebra is actually the Boolean algebra of open and closed subsets of some such space. Yet a different way of thinking about this is that totally disconnected spaces, they have lots of map to finite sets, because whenever you have a disjoint decomposition into open and closed subsets, you get a map to a finite set. And actually, you can completely recover any such guy somehow as the inverse limit of all the maps to finite things. And this means that there's somehow formally just a pro-category of the category of finite sets, which is another purely algebraic way or purely categorical way of thinking of what these things are. So for this reason, we often call these things just pro-finite sets. So, I mean, there's a well-established tradition of pro-finite groups, but you could as well talk about pro-finite sets. Okay. And then the idea in condensed mathematics is to so build up everything just from those pro-finite sets. Or a different way of thinking about this is that you somehow study all your topological spaces or later condensed sets just in terms of how profinite sets can map into them. Yeah, so somehow, yeah. You think of them as being built out of profinite sets, so profinite sets should somehow naturally sit in there, and somehow you remember all the ways that profinite sets sit in your space or map to your space. So, there's a functor. If you have a topological space T, you get a functor that I would call T underlined that goes from this category of profinite sets up, or equivalently these totally disconnected compact Hausdorff spaces to sets that just takes any such profinite set S and maps it to the continuous functions from S to T. So you're really just remembering how profinite sets map continuously into your space. So for example, one very nice profinite space is, or totally disconnected compact Hausdorff space is somehow the space of a convergent sequence. So if you want, it's a one-point compactification of the integers. And then this here would be precisely remembering the convergent sequences in your space. And a basic fact is that this functor T maps to T underlined, it's essentially lossless. So it's fully faithful on what are called compactly generated spaces. And so this includes basically all topological spaces of any practical interest. So often topological spaces are also replaced by compactly generated ones in practice. So this is a very, very mild restriction. So for example, anything that's first countable is compactly generated. And all the first countable things include all the metrizable things. So on such topological spaces, the ones that you see in practice, like doing this thing of just remembering how profinite sets map into them is a lossless procedure. So for example, one key example to keep in mind is that if you have some nice topological space like the interval, then of course you know that there are these counter sets inside of T, these totally disconnected things. But a counter set seems very thin, whereas this seems like bigger than just a counter set. But actually you can also find a surjection from a counter set onto T. So one way to think about a counter set is that it's just product, infinite product of copies of 0, 1. So this would be naturally a profinite set, inverse limit of finite sets. And you can just send a collection of 0, 1s. You can send it to the sum an over 2 to the n. And then because any real number between 0 and 1 has a binary expansion, this is actually a surjective map, right? But then, yeah, some real numbers are not binary expansions, so you need to actually identify a few of these points here. For example, 0.011111 is 0.1000. And then once you make these identifications in this totally disconnected thing, you actually get the continuum. And so something that's always done implicitly in condensed mathematics is to break up nice things like the continuum, to break them up into totally disconnected things like the counter set. Get some water. One second. All right. Okay, and so this leads us to the definition that a condensed set is just such a functor. But actually, not just any functor, but again, you ask that X is a sheaf. So that it's somehow determined locally. And what it means here is that if you have a finite disjoint union of some SIs, then it's just a product of X of C SIs. A finite disjoint union of profinite sets of totally disconnected compact cluster things is still such a guy. And of course, intuitively, it should be the case that if you want to map the disjoint union of all these SIs into X, then this should just be the same thing as mapping all the SIs into X. So you ask that. And there's a further condition that if you have a surjection, if S prime surjects onto S, then, well, what should it... One way to specify a map from S into X is to specify a map from S prime into X. Because this map is surjective, the map from S into X should be completely determined by how S prime maps into X. And conversely, if I already have a map from S prime into X, what's the condition that it should factor over S? Well, it should somehow be the case that the two preimages of any 2 points, if I have a point here, then the preimage should map to the same thing, or slightly better, that somehow that takes a fiber product here, then the two maps agree. So then X of S maps isomorphically to all those maps from S prime into X such that P1 upper star of F is equal to P2 upper star of F. In here. So this is somehow like you could imagine that S somehow has more or less an open cover you have an open cover, and then you take the disjoint union of this open cover to get this S prime here. And then this condition would precisely be the condition that the things agree on overlaps that we somehow had previously when we talked about sheaves. Okay, so that's what a condensed set is, and it's a very algebraic notion. It's just some kind of functor category from this already very algebraic category of profinite sets into sets, and then satisfying some also simply stated algebraic properties. On the other hand, like in practice, like as I said, topological spaces that are compactly generated, they embed fully faithfully into condensed sets. But this here has much better categorical properties. For example, for all condensed sets, we have a mapping object. It maps from X to Y, which is naturally a condensed set itself and satisfies the universal property so that mapping Z into the mapping space of from X to Y is the same thing as mapping Z times X into Y. And this is something that famously fails in topological spaces. So for two topological spaces X and Y, well, you can consider the space of like the set of continuous maps from X into Y, but then there are many different topologies you can put on this. The nicest one probably being the compact open topology. But even for this one, it's not in general true that like a continuous map from Z into the maps from X to Y with the compact open topology is the same thing as such a map from the product into Y. But in condensed sets, it just works. Okay. And it has many, many further nice properties that somehow rectify things that can't be done in topological spaces. So another good thing is that it allows non-separated quotients, non-Hausdorff quotient objects. I mean, it doesn't just allow them. I mean, you can also take them in topological space, but in topological spaces, they are usually very badly behaved. But in condensed sets, they are just nice objects like all the other ones. So for example, if you have, I don't know, a map of topological vector spaces, like say 2 Banach spaces, and you have a map between them, but the map doesn't have closed image. Let's say it's a dense embedding. Then if you want to take the quotient vector space, that's usually a huge mess. It has an indiscrete topology. You can't do anything with it. But you can also take the quotient as condensed vector spaces, and then it's a perfectly well-behaved object. And so for us, like one key fact about this is that if we then pass to a Abelian group objects, so to pass to condensed Abelian groups, so these are some of the analog of topological Abelian groups, and again, compactly generated topological Abelian groups embed fully faithfully into condensed Abelian groups. This is an Abelian category. And somehow, at least since Grothendieck's Tohoku papers, this is like the setting in which you want to find yourself if you try to do some kind of homological algebra. So let me remind you why this is maybe surprising that this could be true. I mean, actually, it has very good categorical properties even within Abelian categories. So it's as nice as just Abelian categories in some sense. And one thing you can do in topological vector spaces is you can take the real numbers with the discrete topology mapping to the real numbers with the natural topology. And this is a map of topological vector spaces. I mean, it's continuous because, well, if you map from anything discrete, it's always a continuous map. But the kernel and the co-kernel. So the kernel is all the elements that go to 0 here. Well, that's obviously 0 because there's nothing in the kernel. Then there's also this notion of the co-kernel, which is where you mod out by everything in the image. But well, this map is surjective, right? So this co-kernel is also 0. But it's not an isomorphism. But in an Abelian category, it should be the case that if you have a map which doesn't have a kernel and doesn't have a co-kernel, that should actually be an isomorphism. But this is somehow totally false in topological Abelian groups, simply because you can't have the same group with different topologies, one finer than the other, and then you always run into this issue. And so how is this rectified in condensed Abelian groups? Well, there I pass to this functor there. And then this actually turns out to be still an injective map. And then there is a co-kernel, let me call it Q. And this is actually non-zero. Namely, if you evaluate what Q is on a profinite set, it's precisely the quotient of the continuous functions from S into here, which by definition are just the usual continuous functions from S into R, but the continuous functions from S into R with a discrete topology are just the locally constant functions. And so, of course, if you just evaluate this on a point, someone just look at the underlying a Being group, this is 0 because, well, if this is just a point, then all maps like continuous or are locally constant. This is R mod R, it's 0. But if you take some larger Cantor set, but for example, the Cantor set that's embedded into the real numbers, then this is somehow continuously embedded, but not in a locally constant way. So locally constant maps, they would have finite image. And so this is very much non-zero if S is infinite. Or you could also take this space of like the convergent sequence, and somehow there are more, not any convergent sequence in the real numbers is locally constant. And so somehow by also remembering everywhere some of the values on all profinite sets S, you've naturally resolved this issue that this map seemed surjective, but was not an isomorphism. Right, it's almost time to wrap up. So let me try to get back to where we came from. So within all, so the next theorem, that's actually pretty hard, is that there exists a notion of what we termed liquid R vector spaces, giving some kind of diagram. So so you have all the condensed R vector spaces, or let me underline this. So you take R with its natural topology and then consider it as a condensed algebra, actually, condensed ring. Then you can consider the modules over that. So this is the condensed R vector spaces. Just like you can define topological R vector space, you can do the very same thing in this formalism. And so as I said, this is very, very close to like topological R vector spaces. In particular, there's a functor that's like very close to a fully faithful functor. And inside here, you have this category that you usually use in functional analysis. You have the complete locally convex ones. And we would like to somehow ask a similar completeness condition on such condensed R vector space, and it turns out that you can. And actually, there is a funny thing that this depends on a parameter p that I will explain shortly. And then there is a natural functor here, but actually it's even defined on p convex ones. That's then somehow also basically a fully faithful functor. Right. Yeah, so 0 p here is a parameter that you can choose that's anywhere between, it's larger than 0 and at most 1. And you can somehow allow somehow non-convex, but somehow only p-convex vector space into the theory, and you actually must. Turns out that if you really ask for convexity here, you run into some issues having to do with entropy. But if you allow this non-convex setting, then you can actually make something that's very, very well behaved. and such that some of this category of p-liquid guys inherits all the niceness of condensed R vector space. So it's an abelian category with many, many, many nice properties, including some kind of a completed tensor product. In particular, there's this very nice class of dual nuclear Fréchet spaces that's in particular sits inside these p-liquid ones. And the tensor here maps to the usual tensor here. Or also on the nuclear Fréchets. So at least on the nuclear objects, it gives you the usual tensor product you know and love of these guys. If you would really work in the setting of Banach space or something like this, then there are already many, many tensor products around. They all agree on the nuclear ones. And so we give you yet another one that's again different on the Banach spaces, but again agrees with the other ones on the nuclear guys. But then this really gives you an extremely nice categorical home for doing functional analysis. And then in the last 3 minutes or so, let me just very, very briefly say how the argument goes for proving the stuff about the holomorphic functions. So this uses some really fancy abstract nonsense. So let's look at liquid vector spaces, which are actually algebras, modules over the polynomial algebra over the complex numbers. And then let's take the derived category of that, or the derived infinity category. Then to this we can associate a certain locale, this basically pointless topological space. So you don't define what the points are, you only define what the open or the closed subsets are. It's some kind of spectrum of this category, which is given by the idempotent algebras the closed subsets correspond to the idempotent algebras. So idempotent algebra means that if you tensor it with itself, you get A. And then just an abstract nonsense gives a structure sheaf on this kind of spectrum in this world. On the other hand, some explicit examples like the holomorphic functions on some disk. So these turn out to be an idempotent algebra, these holomorphic functions on a disk, if you somewhat tensor them with itself, but like really in the sense of Fréchet algebras, nuclear Fréchet algebras, then you get the algebra back. So you just you know that you want to do something with these algebras, and they turn out to be such idempotent algebras in this setting, precisely because we have such a nice completed tensor product. But on the other hand, for the abstract nonsense here to work, we really need that this is a very, very nice category. Okay, so we have these explicit examples, and they basically produce a map from a certain open subset of this locale towards, well, a priori not towards the complex numbers, but instead towards what's called the Berkovich spectrum of this polynomial algebra. But it turns out that the Berkovich spectrum of the polynomial algebra is actually just the complex numbers. So all the points here are given by like putting a value in for t. So you get a map to t here. And this actually, this argument goes back to Ostrovsky in 1916. It's a very classical thing. Okay, and so you have the structure sheaf O here. Then you get this on this U, and then you can push it forward here. Then you get some sheaf on the complex numbers, which you somehow produce just by pure thought. Like, well, you just put in these algebras, you observe, oh, there's very little computation involved in this, certainly no integration. So you get a sheaf on the complex numbers, and then more or less by definition, the value on disk will be these algebras of holomorphic functions, and then you're done. Okay. So yeah, let me stop here.
Thank you very much for your talk. Do we have any question for the speaker? I have one. So you said that in your theory you can deal with non-Hausdorff quotient spaces. Right. So in general, in functional analysis, when you don't have an image which is closed, you cannot take the quotient, you cannot do duality and so on.
Right.
Yeah. So in your case, can you do something? Did you think about? Thank you.
Yes, yes. I mean, let me give you one kind of specific example of something you can prove. So there is a very famous theorem in complex geometry called known as serially. And this says that, let's say you have X a complex manifold. And let's say little omega is the d's exterior power is of dimension d, of complex dimension d, of the differentials. And then Serre proves that if all the cohomologies so yeah, if all these complex cohomologies of omega are Hausdorff, then you can compute the cohomology of the structure sheaf as the dual of the complex support cohomology of the sheaf omega. So this will be here a dual nuclear Fichet space, and this will be a nuclear Fichet space. But he could only make a statement when these are all Hausdorff, because otherwise, like, yeah, like, I mean, even this thing here might be non-Hausdorff, the cohomologies of O. So part of the claim is that in this case, these things are also Hausdorff. Yeah, in general, they might not be, but the dual of anything would always be something Hausdorff. So classically, you can formulate a statement on individual cohomology groups here. That's if you have this phenomenon that you have these non-Hausdorff cohomology groups. But in general, if you just treat everything here as a condensed vector space, then, well, you can always form this as a condensed vector space, and then you actually always get a sequence that the cohomology of this maps to the dual here. But then in general, there's one further term, which is an x1 in condensed C vector spaces of the compactly support cohomology in 1 degree lower, I guess. I might have my indices mixed up, but something like that. So you somewhat have the dual here, but you also need to somewhat take the derived dual, so which also introduces the next one, and then you get this sequence in general. And I think to get such a statement, you really need some such framework here. And I should also say that this is somehow very similar to Poincare duality with C coefficients. So in the case where you want to formulate Poincare duality with integral coefficients and you have torsion in your cohomology groups, and there's also some x1 groups that appear when you make this explicit how you compute the cohomology from the compactly support cohomology. And yeah, so, and in this sense, some of these non-Hausdorff quotient objects that you get here, they're only as strange as torsion abelian groups. So you can really work with them. Just like you can work with torsion abelian groups.
Thank you very much. We have a small question from the remote audience. They ask about the fact, can you deal with infinitesimal near points? Some kind of blowing up, real blowing up, I think. That's
infinitesimally blowing up. Well, I was just talking about this this category of idempotent algebras. And we're somehow, they're only using, usually localizing like on the usual complex numbers. But on this locale that I introduced, you could localize much further. You could really go zoom in very closely near a point, or yeah, you can ask very specific growth conditions on the coefficients and talk about some open subsets where the algebra of functions, well, it's still given by some power series expansions, but it's actually power series expansions that don't converge at any single complex point. They are just some kind of more like formal things, but where you ask very specific growth conditions. So in this sense, you can really talk about, I mean, yeah, on this locale, if it had enough points, there would be some points that are infinitesimally close to usual complex points, but not identical to them.
Okay, thank you very much. There is a, yeah.
Okay, hi Peter, it's Francesco. Yes, so you have brought a revolution in the field of arithmetic geometry with the theory of perfectoids. Now, like 2-3 years ago, you brought another revolution in a even more broad field, which involves topology, analytic geometry, functional analysis in all type of ambience. So my question is very simple. So do you have any other surprise hidden, and are you ready for something else?
No, currently I'm just trying to understand this kind of stuff. And,
Thank you. Do we have a... I have a curiosity, Peter, for you.
Yeah.
So there is a long-standing ideas of finding this category of motives. It looks like that you are making bridges between realization. Do you care about the motives of this of this category? Thank you. It's a meta question.
Yeah, I mean, right. I mean, there's this traditional philosophy of that motives should somehow be like some kind of free construction starting from schemes, and then you somehow make it into a being category, and then you try to prove things about it. This is not how I try to approach this, but I really try to, by hand, find the explicit universal cohomology theory in some sense. And so there are some ideas like how the universal cohomology actually, what kind of structure it should be. And I mean, I wrote this philosophy in my ICM report about this kind of Stukas over spec Z, and that somehow a motive should be some kind of Stuka over spec Z. But I mean, so far this doesn't really make any sense. It makes some sense over the periodic numbers, and in that case, it's very much related to periodic Hodge theory and everything with the Falk-Fontaine curve and not. And I hope that somehow in complex Hodge theory, there are similar hints for what somehow Stuka should be near the real numbers, near the complex numbers. But so far, I mean, I think it should be related to the stuff about twistor theory. I mean, Carlos Simpson has this reinterpretation of Hodge theory in terms of twistor theory, and then Takuro Mochizuki now has done some really fantastic work that uses these ideas. And there seems to be this analogy between this twistor P1 that appears in this complex theory and this Falk-Fontaine curve that appears in the periodic theory. But it's so far, I just don't understand it. I mean, this is something I would like to understand.
Thank you very much. We don't have any more questions for you. Thank you very much, Peter, for your talk. Thank you.
Thanks. Thanks for the invitation.
And after this, there is that coffee break on the other room. Thank you very much. Thank you. Thank you again, Peter.
Bye.
Not for
Thanks.
you, coffee break.
Cominciamo a collezionare la... non devo capire.
Okay, please take a seat. That we resume our program. So let me call Pierangelo Marcati, the chair, on the next speaker of today.
Thank you. Today, I am really pleased to introduce Camillo Dell'Ellis, that I know since he was probably finishing his PhD in Scuola Normale, and it was still clear from there, that time, that he would be a unique mathematician, the unique mathematician that you know now. Camillo is presently a permanent faculty member at the School of Mathematics at the Institute for Advanced Study in Princeton, where he was appointed in 2018, succeeding Professor Emeritus Thomas Spencer. Camillo graduated at Scuola Normale, as I mentioned before, in 2002 with Luigi Ambrosio as doctoral advisor. He then was postdoc. He was postdoc at the Max Planck Institute and at the ETH Zurich. And later he served as a faculty member of the University of Zurich from 2004 to 2018, when he was appointed in Princeton. Camillo is known to be to have a very broad set of mathematical interests. I was joking with him before that to present his mathematics, I would do a separate conference by myself. So, in some sense, let me briefly summarize what he has done fundamental results in geometrical measure theory, in particular regularity theory of minimal surfaces, and he was characterized because he reopened all the question of regularity for minimal surface in general codimension. You know that the Italian school had a relevant contribution in codimension 1 due to the Giorgi, but the general codimension was studied in a famous big regularity paper by Almgren, and Camillo reattacked all the questions in that paper with Spataro. He wrote a series of papers with Spataro, where, you know, from a paper of 1,000 pages, difficult to get inside, you have now a present theory that is achievable, reasonable, readable by the many mathematicians. And in doing that, he settled some open question left by Chang, so the theory now, the regularity theory is more complete. And in the recent period, Camillo and this group attacking the boundary problem of boundary regularity, but this is probably what he's going to talk about today. So let me also mention that Camillo has done a relevant contribution in fluid dynamics. Particularly, his intuition with Laszlo Tseklidi was related to the connection of the work of Nash and Gromov on Nash-Kuiper theorem and embedding of manifolds, and to use the same methods in fluid dynamics. Onsager conjecture, roughly speaking, says that if you have a solution continuous in time and elder continuous in space, you have a threshold phenomena that happens when the elder exponent is 1/3. So the positive case, the conjecture is related to conservation of energy. So you have that a positive answer that was done by Eink, then later by Konstantin E. and Titi, and the big question remained open was what happens when alpha is less than 1/3. And in this case, they started a series of a paper that, with in collaboration with Laszlo Tseklidi, and the whole question was settled by a series of a paper that I can mention Camillo, Laszlo Tseklidi, and Laszlo and Sara Daneri, and then at the end with the conclusive paper of Iset. So there are many other things that I could mention in the mathematical activity of Camillo. Since I come from the field of conservation law, I have to say that also he touched the field, although it was not one of his main interests. He made important results even there. And he received, because of this activity, let me also mention that recently they started a seminar in Princeton. They have done, I think, the past year, a seminar in Princeton concerning problem of no uniqueness for Euler and Navier-Stokes related to the work of Wyszynski. So Camillo, because of all this activity, received many prizes. I'm sure that I'm missing many, but let me mention the most relevant one. The most relevant one, you have the Stampacchia Medal in 2009, the Fermat Prize in 2013, the Cacciopoli Prize in 2014, and the Boker Memorial Prize in 2020, and then he was also invited as speaker in ICM, in the ITD Rabat, plenary speaker at the European Congress of Mathematics in 2012, and plenary at the virtual ICM that unfortunately will not be held in St. Petersburg this year. Recently also got the Mariam Marzacani Prize in Mathematics from the National Academy of Science of the United States. Let me conclude this presentation, because I took too much time, that I am very happy to, I have an additional reason to be happy to present Camillo, that he is in the board of advisors of the PhD program in my school in GSSI. So thank you very much. So Camillo, the title of the talk of Camillo, as you can read, is Boundary and Regularity of Minimal Surfaces.
Thank you. Thank you very much for the invitation, for the beautiful introduction, and for giving me the opportunity to speak in this wonderful and kind of intimidating place. Okay, so my talk, as it was anticipated by Piero, is about the boundary regularity of minimal surfaces. So, so here, let me start with the classical problem of plateau. Given a one-dimensional contour in the Euclidean space, in our three-dimensional space, you're interested in the surface. Actually, the surface is not necessarily unique, so maybe in a surface which minimizes the area among all the ones which span this contour. So it's a famous problem which was proposed by the Belgian physicist Joseph Plateau at the beginning of the 19th century. And he proposed it because he was interested in modeling the shape of soap films. And so here what we mean, right? So you can take a wire, which is, for instance, made of metal, but actually it works even with other materials. You dip it into a bucket of soapy water, and when you take it out, you will see, it's probably going to be difficult in here, but it will be easier in here, where you see a diffraction effect of the thin film. So you see a film formed by the soapy water, which is essentially attached at the wire. But in fact, in the mathematical literature, the minimal surfaces appear as early as, not 1960, sorry, this is a typo, as early as 1760. And it appears with the birth of the calculus of variations as we understand them today. So it appears in this paper by the French mathematician Joseph-Louis Lagrange, which is one of the papers in which he laid down the foundations of the modern calculus of variation. So how you compute, in particular, an Euler-Lagrange equation for a functional, okay? So it's in this paper over here, and when I was actually preparing this talk, my attention was captured by the place in which it was published, Miscellanea Taurinensia. In fact, as I encourage every Italian mathematician to know, Joseph-Louis Lagrange was born as Giuseppe Luigi Lagrangia in Torino in 1736. I actually mentioned this casually at a lunch at the Institute for Advanced Study, and the people in front of me didn't know that. And they told me, well, yeah, okay, sure, maybe he was born over there, but you know, he must have done actually all his important work in France. Well, not really. So he was actually in Torino till 1766. And this paper appears in 1760 in this Miscellanea Taurinensia, which is actually a journal that he founded. So now, okay, maybe there's a problem. That would be a problem today with peer reviewing. But anyway, so he founded that journal together with his pupils. And it later actually was merged into the proceedings of the Royal Academy of Sciences of the Piedmontese kingdom. But in fact, in 1766, he moved to Berlin. Then he moved to Paris in 1786, sorry. So at the age of 50, which tells you two things. So it's good to facilitate the immigration of people in a new country, as the French did with him, and to naturalize them, so that you can later claim that they are French, for instance, or I don't know, Italian. So anyway, it's in his work, he actually shows how to compute the Euler-Lagrange equations for extrema of integral functionals, what we call today Euler-Lagrange equation. And actually, the biggest part of his work is reproving the solution of Bernoulli of the characterization of the Brachistochrone. And he also does other things in one dimension. And then, in the appendix, he uses this method to find the equation for minimal surfaces, the first instance in which this equation appears. And it might be the first instance in which an elliptic partial differential equation appears. It appears before the Laplace equation, apparently. So here's the paper, and now I don't know if you can see my pointer, right? But this guy over here, so this is the start of the appendix. This guy over here is the area functional. So this P and Q, it's a function of two variables. This P and Q are the partial derivatives in direction, say, x and y of a function, okay? So it's difficult to read, but you don't have to read it. You just have to believe me, because I'm going to copy a part of it later on. So here is where he derives the partial differential equation, which is a little bit harder to recognize because there's no partial derivative, right? So, but the partial differential equations are actually in this line over here. So if you cannot see my pointer, the partial differential equation appears on line 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'm actually going to copy it here because it's wonderful how he actually states them. So he states the PDE by just saying the following. You take the differential form P dx plus Q dy, and you take this other differential form, and the condition is that they are exact differentials. Now, if you explore, I mean, if you expand this condition, so the first differential to be exact, it actually has to be the differential of a function, right? Because it's a one form. So then P is the u dx and Q is the u dy. And when you actually unravel the condition of exactness of that one on a simply connected domain, which simply means that you can actually take the divergence of a corresponding vector field, you find this one, the equation of minima surfaces. It's entirely equivalent on simply connected domains. Okay, so now here actually I'm going back to Plateau's problem, which I found out actually he was a son of immigrants of Italian immigrants in Belgium, so his real name was Giuseppe Platone. No, I'm joking, I'm joking. It's a joke. So, but I'm going to state it in a way which is kind of more general. So I'm actually interested in an m-1 dimensional surface gamma, potentially in an ambient Riemannian manifold, on which I have to make some assumptions. And then I'm interested in finding the m-dimensional surface sigma which bounds gamma and has least volume, okay? So now, even though all I'm going to say mostly works on a general Riemannian manifold, in practice, I will actually focus on the Euclidean space, just to make things simpler. But from time to time, I will mention something which maybe I can only prove in a Riemannian manifold. I mean, like, for instance, if I'm going to find for a negative result, somehow having a varying Riemannian metric makes my life a little bit easier. And there's the tenet of, like, you know, all of this business that if something is true on the Euclidean space, you're going to actually get it in the Riemannian manifold with an effort which is maybe 10–15% of technicalities more, something like that. I mean, if you look at the length of the papers, I think that's an accurate estimate. Okay, so now here is the first fundamental question. So what do we understand with the words surface, with the word bounds, and with the word volume in this case? Okay, so there's a very classical answer by Douglas and Rado in the beginning of the 20th century, and Douglas got the Fields Medal for this. So you just fix an abstract manifold sigma prime, and you look at maps which are going from sigma prime into target M, and you just impose that when you restrict this map to the boundary of the abstract surface, you have an homeomorphism with the surface you want to span, which is gamma. Okay, now that's very nice, but it has limitations. It works only on two-dimensional surfaces. There are actually even just counterexamples, and there's problems in higher dimension. And it also fixes the topology of your surface. So, I mean, like, it allows you to find, say, the minimizers among all disks or among all surfaces of genus 1, for instance. But if you're interested in everything, or possibly even surfaces which are like of infinite topology, that is not going to be good. So geometric measure theory, which is a great subtopic of the calculus of variations, offers, in a sense, two general philosophies on how to answer this question. I mean, how to determine what is the set of competitors. So, first of all, let me just address what I would call the set theoretic philosophy. So this is pioneered by Reifenberg in 1960. So in the set theoretic philosophy, I'm just going to tell you this. My competitor sigma, the class of surfaces over which I actually minimize, is just a set, a closed set, actually, typically. And now the volume is just a measure which allows you to measure the volume of all closed set. If it is m-dimensional, I mean, if the m-dimensional volume is finite, you're happy. If it is infinite, well, it's there, but anyway, you're going to minimize it. So things which are infinite are not going to be so interesting. And the typical choice is the Hausdorff measure, for instance. But you might take actually other choices as long as your measure coincides with what you expect to be the volume functional on nice sets. Okay, then you have to tell me what it means that gamma is bounded, I mean, that sigma bounds gamma, okay? And typically this means that there is some topological notion that makes gamma trivial in sigma. This topological notion might change, and for instance, in Reifenberg's original work is that the Chesh homology of gamma is, I think it's actually the Chesh cohomology of gamma is trivial in sigma. Okay, that's one approach, but I'm not going to follow that approach. There's another basic philosophical approach, and it's functional analytic. And I think the first instance of this is actually the Giorgi in the 50s. So here, you just fix a class of desired set, sigma, the ones you like. And on these guys, you know what it means to bound something, and you know what it means that the volume is equal to something. I mean, for instance, smooth surfaces, let's say. Okay. In the specific example of the Giorgi, he took boundaries of open sets. Now you decide the topology on these sets. And once you decide the topology, you complete the space. Now this space has more objects, and how do you define the boundary on those objects? Well, I mean, like, you know, you completed the space, so you have a closure. You hope that your boundary is like a continuous operation. And how do you define the volume? Well, you extend the volume, hopefully, to be a lower semi-continuous function. Hopefully. Of course, that is only going to be correct if you got a good topology to do this. And you're only going to have some existence theory if the setup is amenable to the direct methods of the calculus of variations. That's why, for instance, you would like to have a lower semi-continuous functional. Okay? So, okay, so this is like the prototype philosophical approach that I want to take, and let me just go into one of the most successful functional analytic approaches, which is the Federer-Fleming theory for the oriented plateau problem. That's what I'm going just to present. So you start with sigma, which are usual singular chains with coefficients in some norm groups. If you're a bloody analyst like me, this just means that you have p's, finitely many p's of nice surfaces with boundaries, which are nice. They are oriented surfaces, and you just put some coefficients on it. And if you're an analyst like me, it's okay. You know the integers, maybe the reals, the complex numbers, but that's it. So I'm just going to put actually in this example the integers, but you can put other groups. Okay, so now here, that is what this is, right? So the sum, the formal sum of ki sigma I, where sigma I is the image of an m-dimensional simplex, for instance, through a smooth map, okay? So now you have the boundary, which is the usual operation you know. And you have the volume, which is the usual volume, because these guys are just smooth sets, okay? Just pay attention that you have multiplicities. So if you take 2 times the same surface, then you should count that volume as twice. And pay attention that there might be overlaps between the pieces. Okay, if they overlap, adjust your formulas, okay? So now, what is the topology that you're going to put over here? So there's a very natural topology, which would require a kind of more technical definition, but the things in which we are interested are surfaces which have the same boundary, right? So let me tell you how the topology would work what is the distance that I put between 2 surfaces if they share the same boundary. So I just do the following. So I take sigma 1 and sigma 2, 2 chains with equal boundary. Well, I am in the Euclidean space. Then sigma 1 minus sigma 2, they bound another chain with higher dimension, on which I can compute the higher dimensional volume. So the distance between sigma 1 and sigma 2 is the infimum of the volumes of lambda, because you have to think that sigma 1 minus sigma 2 is a cycle. I can fill it with something, and then I'm just trying to find the filling, which is the lowest. Okay, so it's very natural. Okay, so the completion is called the space of flat chains, and useful actually for our plateaus problem is a nicer subspace, which is the subspace of integral currents, which I can actually use because I fix the boundary. The boundary cannot change, right? So, but in this theory, you can even change the boundaries. So what is the space of integral currents? So an integral rectifiable currents consists essentially it's just a little bit further than taking like singular chains. So I allow you to take countably many pieces, and I allow you to take nasty sub-pieces of your manifolds, okay? So now you can take a Cantor set instead of taking like, a nice piece of your smooth manifold. I only allow positive integer multiplicities because I take oriented surfaces and, if by chance you actually stick there a negative number, I just flip the orientation of the surface. Now, the volume is what you expect is going to be the volume. That is the sum of the volume of the pieces times Ki, except I need to take them so that they don't overlap, okay? But I can actually stick that into the definition, okay? Now, a current is an integral current if both the current and its boundary are integer rectifiable, okay? And that's the setup in which the foundational paper by Federer and Fleming in the 1960s tells us that you can actually solve the plateau problem by the direct methods of the calculus of variations, okay? So now, do we really need this though, right? So one thing that I'm always like, skeptical about introducing a very abstract and complicated theory is whether, do I need to do that? I mean, I just want a nice surface which is minimizing the thing, like, like at the time of Lagrange. So why do I have to go through this? Well, you actually need it because minimizers, area minimizers, can be singular. But I mean, pay attention, it's not that they are singular because I've chosen a singular situation. Even if you choose the nicest class of surfaces, you actually end up with singular minimizers. So there is this beautiful theorem, famous theorem by Bombieri, De Giorgi, and Giusti, which tells you that this 7-dimensional cone, which is split explicit, is the cone over S3 times S3, is an area minimizer for its boundary in this following sense. So if I count out, if I take a unit ball, I mean, this is an infinite cone. I take a unit ball, I intersect a unit sphere with this guy, I find a perfectly smooth boundary, I find an S3 times S3. And this one is the unique area minimizing current, which actually tells you that if you take a smooth surface with the same boundary, that is going to have strictly larger area. So, and since you can approximate it with smooth objects, if you're just trying to minimize among smooth objects, you don't have a minimizer, okay? A minimizing sequence is converging to this guy. Now, you can do the same in codimension 2. So this is codimension 1 surface. And this is a theorem by Federer. And the examples are much easier to write down. So essentially, by a discovery of Federer, which was based on a key computation by Wirtinger, any complex surface, any complex any holomorphic submanifold of a Keller manifold, actually, is always area minimizing. So you can just take your favorite, whatever, algebraic surface or algebraic line, in this case, as the algebraic geometer would say, complex line in C2, which you identify to R4, and that guy is going to be the unique area minimizer. Okay? So you do need it. Okay, so now here's what regularity theory is. So regularity theory is simply the following natural question. So you've got your minimizer, which is built out of the direct methods of the calculus of variation. But it's pretty bad in general, because it's made by these scatter pieces. You have examples of singularities, but you might wonder, whether there's some extra assumption or some extra conclusion that you can draw from being a minimizer. So you should be better than just, a general element. So here are the natural questions. So where can you actually expect, and when can you expect that the minimizer is regular? Okay? Away from its boundary. So this is like, the interior regularity question. Then there is the red question, which is what I'm going to be interested in this talk, which is where and when is an area minimizer regular at its boundary? So where actually, at which points of the boundary, it looks like a nice submanifold with the usual logical concept of boundary. And, maybe there are singularities, but you can ask how many of them there are there, how large is the set of singularities, and then you can ask more refined questions like, how do the singularities look like? Can I study them explicitly? Okay, so this is a beautiful theorem which summarizes, not completely, I mean, we know actually more things, but the state of the art of interior regularity theory. So if you minimize in the sense of Federer and Fleming, the set of interior singularities has codimension 7 in the surface. So we had a 7-dimensional surface with a single point, which was singular. That's the most damage you can actually do for hypersurfaces. And in higher codimension, the set of singularities has codimension 2 in the surface. So again, if I give you a 2-dimensional surface in R4, which is minimizing the area, and has a singular point, that's essentially the worst I can do, okay? And that's exactly what was mentioned by the example of Federer. Okay, so now boundary regularity theory is actually not as developed at the moment as the interior regularity theory. And that's what I'm going to talk about. So now, let me just give you the setup and just fix a couple of keywords clearly, because I'm going to use them for the rest of the talk. So I'm always going to use this gamma, well, always is maybe a promise I shouldn't make, up to my mistakes, for a smooth-oriented n-1 dimensional surface which does not have any boundary in the Euclidean space. That's my boundary. I mean, that's the metal wire in Plateau's original problem. I might be in a Riemannian manifold, but, well, most of the times I'm in the Euclidean space. Now, Q is a positive natural number, because in the theory in which I am, I can actually take this boundary with higher multiplicity, right? That's one possible setup. And then T is what I will call my area minimizing current, whose boundary is going to be this integer multiple of my surface gamma. And okay, in GMT we like this notation with the, these two fancy brackets over here, just to tell you that, well, okay, so as long as it's a surface, I write gamma, but when I understand it as an element in this space of currents, then I just put the brackets, okay? Okay, so now I have these two parameters, right? Q and N, the codimension. I'm going to ignore the dimension, actually, of the surface. We'll mostly focus on these two parameters. So multiplicity means how large is this Q? So the real big difference is between taking Q equal to 1 and taking Q larger than 1. So multiplicity 1 and higher multiplicity. And what also makes a difference in our life is the codimension of the minimizer. If it is an hypersurface, the codimension is 1, n is equal to 1. If I say higher codimension, then n is bigger or equal than 2. So for me, n equal to is higher codimension immediately, even though it's not that high. And there's a, as these two parameters jump between 1 and something bigger or equal than 2, they create a lot of complications, okay? So here is the most beautiful situation that you can imagine. The multiplicity of your surface, of your boundary, is 1, and you are in codimension 1. Then there is this fantastic theorem by Hard and Simon in 1980 that tells you that at the boundary you are fully regular. So there's no singularity happening. So remember that we had this singular point in the cone, right? Well, that has to happen inside. There's nothing like that at the boundary. Now, this was predated by a theorem of Allard in 1969, his PhD thesis, and I'm going to explain you what actually he did in his PhD thesis, and some other papers by Allard which were also fundamental, so one in 1975. But now let me just tell you one thing. So regular boundary points are actually quite subtle. So here's the subtlety. So here there are two simple examples, right? So I take as my gamma a pair of circles in R3. In one situation, the left situation, they are oppositely oriented, and they are very close, okay? Then the minimizing surface is very well known. It's a piece of a classical surface which is called catenoid, okay? And you see it on the left. But if I take the orientation of the two circles to be the same, I mean, you see these little arrows over here, right? So they are the orientation. Then actually the minimizer is two disks. It's never going to be the catenoid, okay? And it's the orientation that forces you that. Now, if I move the upper disk towards the lower disk, I have two sensible situations depending on how I have oriented my surface, my boundary. So on the left, the catenoid is collapsing into a corona, the outer disk minus the interior disk. On the right, the surface is collapsing to the outside corona, counted with multiplicity 1, but the interior, I'm going to get the disk, counted with multiplicity 2, because the top disk is collapsing on the bottom disk with the same orientation, okay? So now, what is the conclusion that we draw from this? Well, we draw from this conclusion, I'm going to use this buzzword. So the Plateau's problem admits two-sided boundaries. So a point which is sitting in here at the boundary between the black disk and the shadowed corona is a point in which I have a boundary there, but I see my surface which is on this side and also on this other side. And the way I pick up the boundary is because there's a jump in the multiplicity, right? So I jump from multiplicity 1 to multiplicity 2. That's a two-sided boundary. And I understand that the two-sided boundary is really regular if locally it can be modeled in the same way as this situation. So I have a single surface, my boundary is sitting on the single surface, and when I walk towards the boundary, I jump from Q to Q plus 1, or from K to K plus 1, okay? If the boundary has multiplicity 1. Okay, so as I said, at the two-sided boundary point, T and gamma lie locally in a single minimum surface. Now, it might happen, but it's very rare. Because a minimum surface is real analytic in the Euclidean space. And so what is the chance that the curve that you take, which is only somewhat differentiable, is going to sit into a real analytic surface? Well, if there's a formula, certainly. But if it's just a generic CK surface, then no. Okay. So gamma divides it into regions, and there is the jump. So this is just an explanation of what I was saying in words. So now, what happens if you have higher multiplicity, but codimension 1, okay? So then there is something for which I cannot give you a reference, a folklore theorem, which allows you to decompose your current into sum of currents which are all area minimizers and take the boundary with multiplicity 1. So I can decompose it into simpler pieces and actually appeal to Hart-Simon, okay? There is no such decomposition in higher codimension. That's impossible. So, and this is due to an example by L.C. Young in the 1960s. It's impossible even for a minimizer. That it is impossible for a general surface, that's easy. But that it's impossible for a minimizer, that's much harder. So let me give you an intuition of what happens. So here, a cartoon picture on how you take the decomposition. So you have your a smooth boundary, right? And here I see a piece of it in 2 dimensions. So these are lines, right? So I have one line with multiplicity 4, one with multiplicity 3, another one with multiplicity 1. And let me just do the following. So let me now assign numbers to the regions in the 2-dimensional space in which these guys subdivide. So I start with 0, and then I walk, and I pick the line with boundary 1 with that orientation, so I jump by 1. And then I walk over to the next region, but the orientation is opposite, so I jump by 3 but down, and then I put -2. And then I jump again by 4 over there, and I jump to 2. So I can attach to this current T an integer valued function f, which in fact is the 2-dimensional current in the Federer-Fleming theory, whose boundary is given by this guy. And I say D because in codimension 1, the top dimensional currents don't have actually much flexibility. So now I can take the level sets of this function. And the level sets of this function are sets, and their boundaries are counted with multiplicity 1. And the folklore theorem, which is called co-area formula in this case, and it's much more general, tells you that each of these boundaries have to be area minimizing by itself. Okay? Okay. Now, what about multiplicity 1, but higher codimension? Well, singularities can actually occur. So here is an instance. You have a half of a disk. So this is in complex coordinates. So half of a disk lying on a 2-dimensional real plane, which is also a complex line. And another full disk, the disk Z1 equals 0, which is again a piece of the complex line, okay? So now they have an intersection at the origin, although they intersect themselves transversally. And the origin is a portion of the boundary, okay? So sigma intersected with B1 is actually area minimizing, okay? And the boundary of this current is a full circle, and then half a circle and a line which is passing through 0. And 0 is a singular point. But I have actually much nastier example. So I'm going to carve an example which is nasty on this complex curve. Again, in the complex space. So now I cannot draw 4 dimensions, but the vertical axis you have to imagine is the complex numbers. And now the plane instead, it's really the Gauss plane for complex numbers. So you see that the real part is actually the vertical, the vertical axis on the plane, and the imaginary axis is actually the horizontal axis on the plane. So on my surface, which is branching, I'm going to cut out a curve in the following way. So I start with this branch, I go around, then I get back over here, then I go here, and then when I actually get on this other branch, I go through the origin, which is the branching point, and I jump to the other branch in such a way that I can actually close a loop, okay? So now this curve cuts out an area minimizing surface in my complex line, or, you know, for an analyst like me, in the 2-dimensional surface, which is also, by chance, an algebraic subvariety of C2, and it's area minimizing. And you can actually, so, you know, this curve gamma, which is like this piece in which I'm joining, you know, -1 minus I to the power q to 1, 1, I can actually explicitly give you the formula. It's not C infinity, but it's CK. If Q is very, very large, I mean, if Q is 2023, the curve gamma is C 1011, okay? So it's pretty regular. And that point over there, sitting in the middle, the origin, is a singular point for the minimizer. And it's two-sided. See, I mean, the surface is on your left, but it's also on your right. So it's a two-sided irregular point. Okay, so now Allard's regularity theorem, which was proved in 1969 in his thesis in codimension 1, and in 1975 in any codimension, tells you that if I give you one additional assumption, which is not that bad, that is that your submanifold is lying on the boundary of a convex set, then that craziness cannot happen, right? Because, you know, I have to do this kind of knotted, complicated curve. So if you give me a curve in S3, in R4, the minimizer is going to be regular at the boundary. There's no foul play over there, okay? And you can see what is actually the game over here. You are at the boundary, and there is a very easy convexal property. Your surface has to be inside the ball. And the convex boundary acts as a barrier to the two-sidedness. So in a sense, a much more general theorem by Allard, and this is this 1975 theorem, tells you that if you're one-sided, I mean, if your surface is not going on the other side, and your boundary has multiplicity 1, then it's regular. Okay. So now, what happens without a convex barrier? Well, this becomes much, much harder. Even the existence of a single regular point in a general Riemannian manifold was open. So together with Guido De Filippis, Jonas Hirsch, not Hirschi, and Annalisa Massacesi, we proved this. So at least in full generality, in any codimension, but with multiplicity 1, the set of boundary regular points is open and dense. Open is obvious. I mean, like, you know, if the point is regular, then everybody nearby is regular. So the important point is dense. So now, you know, this is sort of a lame theorem, right? Because it tells you this denseness is like, you know, the cheapest way to tell you that there is at least one regular point, well, because it's dense. So it's sort of lame. I'm not even going to tell you how painful it is to prove it. That makes it even more lame. But in fact, it's close to optimal. And that's what surprised us. So in the same paper, we give an example of a one-dimensional curve gamma in R4, which is C infinity, and an area minimizing current T, whose set of boundary singularities is actually one-dimensional. So you can go up to 1 dimension. It has 0 one-dimensional measures. So the non-optimality is in the difference between being dense and being of full measure for the regularity, but it's kind of close to optimal. Okay, now, this is maybe a challenging, this is kind of challenging. So what is actually missed in, higher codimension, which is not missed in codimension 1? So there's an ordering to minima surfaces in codimension 1. So if I have, say, a boundary over here and a boundary over there, and I have the minimum surfaces for the two boundaries, they don't touch. If I slide this boundary up, right? So I cannot have a touching point in the interior. I must have a touching point at the boundary. And the Hopf maximum principle also tells me that when I touch at the boundary, I must have two different tangents. I cannot touch at the boundary tangential. Okay, so that's a beautiful PDE fact. It's missed in higher codimension. And what you can do is you can do something like this. You can take a circle, then you can take a sort of complicated curve, and you can slide up the complicated curve and make in such a way that the complicated curve is really touching the circle at many, many, many points, like, because it's just a C-infinity curve. And you can arrange your two minimizers in such a way that the union of the two minimizers is still a minimizer. And the second minimizer is touching, on all of these like crazy points, and those are all irregular points. But you cannot do it on an open set. If you do it on an open set, then the two minima surfaces actually all of a sudden they have to stick together, okay? Which means that the whole curve would have to be over there. That's a loose explanation. These singularities are mild anyway, right? So because I'm always able to decompose the surface into a nice surface without boundary and another nice surface which is taking the boundary. The only complication is in the way they actually touch each other. So Bill Allard would just tell me this is like, C-infinity misbehavior, okay? So there's actually a worse example. Because we can make a sequence of boundary singularities which are actually branching points accumulate to one point, right? So these are actually genuine singularities because you have branching. And they can accumulate inside the boundary. But okay, so the best we can do is an infinite set somehow. For one-dimensional curves. We cannot do something with very large dimension. We're not able to engineer that. Anyway, incidentally, so this actually makes something interesting. So it's actually possible by a modification of this idea by myself, Guido, and Jonas Hirsch to produce a C-infinity closed Riemannian form manifold and a C-infinity closed curve gamma, which bound a unique area minimizing oriented surface which has infinite topology. So if you solve the Douglas-Rado for this particular curve, say with topology, say the disk, there's a higher genus surface which does better. And if you fix that higher genus surface which does better, then there's an even higher genus surface which does better, and so on and so forth. So notably, this cannot happen in codimension 1. So in R3, the Hart-Simon theorem plus the interior regularity theory tells you the solution that you find with the area minimizers is going to coincide with the Douglas-Rado once you pick up a sufficiently high genus for the model of your Douglas-Rado solution. Okay. So some conjectures. First of all, for multiplicity 1 boundaries, boundary singular points have 0 n-1 dimensional measure. That's what you could expect. We don't know how to prove that. Of course, the other thing that you can actually conjecture is that our example is made by singularities which are not too bad. So true singularities, maybe they have codimension 2. This is also likely, I would say. This is a conjecture by White in 1990, and that is what I mentioned by Bill saying, okay, so all of this is a C-infinity mischief. So this conjecture says if you have a two-dimensional area minimizing current with a boundary which is a real analytic curve, then there is no boundary branch points and the singularities are isolated at the boundary and in the interior. So they're going to be 20, 25, but then that's it. And in fact, there is a theorem by White which actually tells you that you just need to show that the surface has finite topology, and then there are no branching inside, and there are finitely many singular points. So this example that I gave you with infinite topology in the case of C-infinity somehow is telling you that really there's a difference between C-infinity and real analyticity for this conjecture over here. Okay, so now here we're getting to the very last portion of my talk. So there's something which is completely terra incognita, which is higher multiplicity and higher codimension. So both Allard in 1969 in his thesis, and White later in a collection of open problems in geometric measure theory, which is kind of like, you know, the holy grail of conjectures in geometric measure theory for us in the area. Like, you know, we go around with this little paper, which collects the conjectures of many people participating to a famous conference at the time. So the question is, what happens with higher multiplicity boundaries in codimension, sorry, higher than 1, right? So because I showed you that for hypersurfaces, it's reduced to the hard sign. And nothing was known till recently. And still, even now, very, very little is known. So now let me tell you what can we expect. So consider the union of two parallel circles in R3 with opposite orientation. So something like this. If I arrange the two circles at the exact distance, gamma bounds two distinct area minimizing currents T1 and T2, okay? So one which consists of two planar disks with opposite orientation, and one which consists of the catenoid. It's, you know, if I lower the circles, there's only the catenoid. If I slide the circles up, there's only the two disks. But there's a moment in which the problem bifurcates. So this guy, which is the union of the two circles and the lateral surface, but taken with an orientation which is creating the union of the two disks and the lateral surface, but taken with an orientation which creates two copies of the circles as a boundary. So this one is an area minimizing current. So I cannot hope for any regularity theory unless I swallow the fact that at the boundary point, when I have higher multiplicity for the boundary, I might see two minima surfaces which are coming together. Okay, so my definition of boundary regular point is a point where that is all that happens. You know, maybe there is a single surface which is coming with multiplicity 2. Maybe there are two surfaces which are coming with multiplicity 1, but they're nice. They don't see each other. They only see each other at the join. And they come transversally. They don't come tangentially, okay? That is what I just said. So for me, if I have a multiplicity 2 boundary point, either I have a single, either the minimizer consists of a single surface with multiplicity 2, getting there smoothly, or two of them. And of course, in general, for general Q, I might have many surfaces which are coming together. But of course, there can always be also the two-sided situation, which is the one which I listed over here, right? So the one like the Hart-Simon theorem, which is kind of exceptional, right? So like non-generic situation that I am actually sitting on a single minima surface and I'm jumping by Q now when I'm actually going through the boundary, okay? So now here is the only theorem that I know of, which I just proved with Stefano Nardulli and Simon Steinbrüchel. So if you give me a one-dimensional curve in R2n, and it's sitting on the boundary of a convex set, so by this, I am avoiding any discussion about two-sided boundary points. They can only be one-sided, so the surface is all on one side. Then, everywhere, the surface is smooth. So I only see from my convex boundary finitely many surfaces actually departing with the correct multiplicities so that the multiplicities add up to Q, okay? We suspect actually that the two-dimensional assumption is optimal. And I would advance this conjecture, which is based on an example by Hirsch and Steinbrüchel for harmonic function. So if gamma is two-dimensional and Q equal 2, there must be an example in which there is a boundary singularity, in which I see two surfaces coming together, but tangentially, and not like, you know, transversally. That's apparently a two-dimensional situation. In general, I would conjecture that if I put the convex barrier assumption, the set of regular points must have dimension m minus 3. So this thing that I'm conjecturing, it happens in a two-dimensional boundary. It can happen at one point. I mean, remember, m is the dimension of the minimizer, so the boundary has one dimension less. And now I'm conjecturing that the set of boundary singular points has two dimension less than the boundary, okay? So boundary 2 minus 2, 0. Okay, now there is an intriguing question, and it is, if there is a convex barrier, is the current always locally decomposable in classical smooth pieces? Because the only example of singularity we know is that the surfaces are coming tangentially together, but they still separate. Okay, so now let me give you a 5 minutes, I think I have, since Piero took a little bit to introduce me. So let me just give you a crash slides on the ideas of the proof. So how do you prove this beast? Well, there's a first step, which is classical. There's an Allard's boundary monotonicity formula, which tells you that when I look at my surface, which I don't know any regularity about, I zoom and I homothetically rescale my surface. When I zoom, my boundary becomes, of course, flatter and flatter. If I am at a regular point, when I zoom in, I should see finally the tangent half space to my surface. In general, you actually know that you converge to something which is conical, which is one homogeneous, so to a surface which is a cone, okay? And what is actually nice of the two dimension is that you can fully classify them. And it's, in fact, very elementary. I mean, it has been done in the interior long ago, and you know, in our paper, we did the little exercise of classifying what happens at the boundary. It's very easy. Now, there's a beautiful theorem by Hirsch and Marini in 2018 that actually tells you that that cone is unique. And not only that that cone is unique, but in this distance, which I told you, the rate of convergence towards the cone is a power law. And that's going to be fundamental for the proof. So it's r to the power alpha for some alpha which depends on q and the codimension, in principle. Actually, this power should be pretty explicit. It should be like 1 over q. Okay, so now there's a corollary of this theorem, which tells you that if the tangent cone, which I have classified, and I didn't tell you, but the classification tells me that there are only half planes coming out, right? As I would expect, because I expect there is regularity everywhere. If I see more than a half plane coming out in the tangent cone, the current decomposes into two pieces, which I can analyze separately and have lower multiplicity at the boundary, okay? In particular, I can actually induct the proof on the multiplicity Q. Because when the multiplicity is equal to 1, I have Allard theorem, which tells me that everything is regular, right? So what is actually that I have to understand? What I have to understand is the situation in which I see a tangent cone, which is a single plane. I cannot decompose the current in an easier pieces. And now, if the tangent plane is a single, if the tangent cone is a single plane, the surface better be of full multiplicity and just classical, one single piece coming there. Okay, so how do I deal with this? Well, this is the famous monograph by Angren, which was published in 1980, and which does an analysis of what happens at singular points with a flat tangent cone in the interior. So I'm going to give you a paragraph, which is a summary of this 1,728 pages proof. So there is two things that you're constructing in this theory. So one thing is the best smooth approximation that you can take at that point. And that is what you call the center manifold. And then there's a second object, and this second object is a harmonic multi-sheeted approximation of your current, which is only an approximation, but it's harmonic. And it's genuinely multi-sheeted. So it's not like, you know, it's not a surface collapsed with multiplicity Q, it's at least two pieces. But, you know, it's multi-sheeted, so I cannot separate into separate pieces. I mean, they're kind of, you know, like interacting with each other in a crazy way, like a branching of an holomorphic curve. And now the theorem, the 1,720 pages proof, tells you either the multi-sheeted thing is non-trivial, or the current completely coincides with your center manifold. So your best smooth approximation is the surface. So what you gained at the point, which is singular, but it has a flat tangent cone, is a model singularity that you can analyze because it's an harmonic function. Okay, so now Angren's theory was mentioned by Piero, was reworked by Emanuele and myself in a series of papers between 2009 and 2016. And in the paper with Guido, Jonas, and Annalisa, we actually produced the boundary multiplicity 1 version of this, two-sided situation. And we produced a secondary boundary version in the paper with Stefano and Simon for boundary multiplicity Q bigger than 1 and one-sided situation. What we are not yet able to do is produce a universal construction which is going to address the two-sided situation higher codimension for higher multiplicity, like sort of the best theory that we could possibly have. So now, in this case, if I have this tangent plane which is flat, I construct the center manifold, and then if the point is singular, which I want to show it's not, there is this multi-sheeted approximation which is harmonic. Now I can completely classify it because it's a two-dimensional situation, and it actually happens to be radially homogeneous. That's the hardest analytical estimate, actually. So I can completely classify it because I can, sorry, I sort of swap the order. So I can prove it is radially homogeneous and multi-sheeted harmonic, and then since it's a two-dimensional case, then it's completely classified, it has to be linear. Now, there's one catch. There is a second analytical estimate which tells you linearity and non-triviality would actually imply that the decay to that cone is very slow. Slower than any power. So it could be a logarithm, but not a power. But if you remember what I highlighted in red some time ago, the Hirsch-Marini theorem tells me that I have to decay like a power law. So I cannot decay like a log. So the multi-sheeted approximation must be trivial, which means that my surface coincides with the center manifold and it's regular. And that's all I wanted to tell you.
Thank you, Camillo, for this exciting and beautiful talk, and for the energy that, as usual, you put in the lecture that I think is communicated to the audience. And so, time for questions.
I was wondering about your last slide. You said that the 2D assumption is crucial for this, saying that it's linear, right?
Yes.
So that's the only point, like if you could, I mean, is this the only key step missing, or there is something deeper to go to higher dimension?
No, that's, okay. So, yeah, so that is not going to work in higher, that is not going to work in higher dimensions. So the reason why it's linear is because if it were like, a bunch of other harmonic functions, they would actually intersect. Because, they're going to be sines and cosines. And these harmonic multi-valued functions, they're slightly better than harmonic. They're actually the minimizers, and there cannot be any intersections. Yes, in higher dimension, I don't know how to do that. So there's going to be like, three-dimensional harmonic functions with this trace equal to 0. And now, like, there are some that don't intersect, and and for instance, there are a couple that actually come tangential. And what you might speculate is whether, like, you could, like, take that example and maybe it's minimizing, and maybe deform it to an area minimizing surface. That's what Simon and Jonas actually found out. That's the reason for the conjecture. What fails in dimension 3. Yeah. Oh, of course, what we don't know how to do in dimension 2 is the Hirsch-Marini theorem also. Huh? But okay, the Hirsch-Marini theorem, I think, in like once you have a convex barrier, you can use Leon-Simon's techniques, I think, to get it. In fact, I've asked the student to try to do that.
For a question.
Yes. No, is it? Yeah. Regarding the first conjecture that you displayed, how does it change if you take generic gamma?
Yeah, for a generic gamma, for a generic gamma, unfortunately, we cannot prove anything better. We can exclude for a generic. So for a generic gamma, it's simple to tell to say there cannot be these two-sided boundary regular points, right? Because you've got this very special property that your curve is lying on your minima surface, which is both on the right and on the left. It's just cut by the curve into two pieces. That's a very non-generic situation. So I can tell you like a theorem like, by small perturbation, I can find a new curve, say, and this new curve has only boundary regular points which are only one-sided. But I don't know of a way of using genericity which allows you to, like, get better regularity. Of course, the example that we have in which there is this curve which is touching the surface is very, very, very non-generic. So if I had to bet on a conjecture, I would say, okay, for a generic curve, there's like, I don't know, let's just talk about curve and two-dimensional surface. There's just like, discrete set of singularities if you're very bold. Maybe a dimension 0 set of singularities if you're less bold. Even the example with infinitely many boundary branching points converging to a point, which seems more robust, it's still very unstable under perturbation.
Actually, I have a question related to that example, your worst example. You said there exists a C infinity manifold of dimension 4. Yes. Can you do that in R4, or is there something you need about the metric or the topology of the manifold?
No, I really need to change the metric. So the way we do with the worst example, so that is really, okay, so what we can do in R4 is produce an example in which you have a sequence of, like, singular points which are like intersecting points or boundary branch points and are converging to this point P. But the surface is always a disk. Now what you can do in a manifold, you can take the points of intersections and like replace it with a very small catenoid and make the catenoid, like, becoming smaller and smaller. And then you change the Euclidean metric around this catenoid and patch it carefully in such a way that then the surface becomes a minimizer in this perturbed metric. But I don't know how to stick the catenoid in there because the Euclidean space, unfortunately, being real analytic, is much more rigid. I don't know how to stick like the topology in there. And if I try by hands to construct an example which has topology, because you know that branching points might actually create topology in your Riemann surface, then I don't know. But it might be just simply that I am not good enough with Riemann surfaces, that we are not good enough to actually produce an example which has infinite topology even in the Euclidean space. I would bet that should be possible. So I think it's just an artifact of the proof that we need a Riemannian manifold.
Just a curiosity. When you make the soap film in your second slide with the metal frame inside the bubble, if, for example, you have something like the two circles in R3, how does the bubble film, the soap film, see the orientation if it happens?
So this I should have said from the very beginning. So all of this theory is very beautiful because it captures kind of geometric properties that we like very much. Like, you can represent homology groups, for instance, in general manifolds with area minimizing currents. If you're interested in the actual problem of Plateau, which is modeling the soap films in 3 dimensions, then definitely this is not the most efficient theory to do it. You might want to do something a la Reifenberg. So then in that case, I'm actually not caring about multiplicities. The other way you can do is you can tweak your, you can use the theory of currents and you can tweak your coefficients groups. But then if you ask a guy like me, I would say still this does not capture actually the physics. So this is a separate issue and I would have to make sort of a separate conference. I mean, I have also like, interests in that direction and there's like lots of works in GMT. I think the most convincing way of modeling actually that problem, which is landing into some area minimizing property by, some say, expansion around some physical quantity, because the film actually has a little thickness, and so the area minimizing problem of Plateau does not make sense at physical level. In fact, if you take a bucket which is like as big as this one, like as this room, and you take a wire, you're not going to see actually any any soap film when you actually dip the wire, if the wire is very big. I mean, at a certain point, the soap film does not actually sustain a very, very, very large guy. And where is the problem? Where the problem is at the level of the physical level, the surface is really not like, of dimension 2, is of dimension 3, just one dimension is very small. So there's a beautiful work, recent work by Francesco Maggi and Salvatore Stuvard, and the third person that now I forgot. Shame on me. But these people, they actually nailed down a physical model for how the soap film would behave, and then take a small expansion in the parameter, and they land into a set theoretic problem in the limit in geometric measure theory, which has been proposed in the last 10 years by Jenny Harrison, and which is studied by them and some of us. And there are still very many open questions. And you're perfectly right that this fact with multiplicities is not something which is good for the actual physical problem of Plateau. Right.
Other questions? Okay, thank you.
Okay, so we will resume at 2:30. Now we go to lunch.